Okay, in this podcast we're going to talk about polar covalent bonds. So if I have a covalent bond, let's say it's between a hydrogen atom where I'm sharing two electrons, chances are, because they're the same atom, that the electron cloud is going to be pretty even around, or the shared electron cloud is going to be pretty even between the two atoms. However, if I have two different atoms, oxygen and hydrogen for instance, oxygen is more electronegative, right? We talked about electronegativity last unit. It means it's the ability of an atom to pull electrons towards itself. Then what's going to happen is this electron cloud is going to be denser around the oxygen than it will be around the hydrogen, because the oxygen is able to pull the electrons more towards itself. And therefore we have what's called a polar bond. So if you remember, the electronegativity is the ability of an atom to pull electrons towards itself in a covalent bond. Okay, and if you remember, the high on the periodic table was fluorine. So here we have an HF bond, and because fluorine is more electronegative, the density around fluorine is going to be higher. Now there's two ways to represent a polar bond like this. One is to use this arrow symbol where the arrow points towards the more electronegative side. And if you put a hash mark here, then it makes this be the more positive side. The other way to show it is to use the delta plus and the delta minus, which indicates that this side is a little more positive and this side is a little bit more negative. It's not a full positive and full negative like in an ionic bond. It's a partial positive, partial negative. So how do we determine what type of bond we have? Well, for an ionic bond it's pretty easy. If we have a metal and a non-metal together, we're going to have an ionic bond. Okay, and one's going to be positively charged and one's going to be a full negative charge. If we have two of the same atoms, it's going to be a non-polar covalent, right? Because those electrons are going to be shared equally. All right, so we have lots of examples. All the diatomic elements are going to have a non-polar bond. They're going to be shared, electron pair will be shared equally between the atoms. Okay. Now there are also a couple of cases on your periodic table you can find the electronegativities. If you look on the green sheet, and there's a number on the lower right hand corner, if you look at fluorine it's 4.00, that's the electronegativity value. And it's an arbitrary value. Fluorine was set as 4, everything else is compared to fluorine. But if you look on that table, you'll see that, for instance, C and S both have a value of 2.5. So even though they're not the same atom, they're going to pull equally on that electron pair that they share. So a non-polar covalent bond is when there's no difference in the pulling ability or the electronegativity of the atoms, or essentially no difference. Okay? So a polar covalent bond is when the atoms pull differently. In this case, oxygen is more electronegative, so the electron cloud is going to be a little closer to and denser around the oxygen than it is around the nitrogen, making the oxygen side more electronegative and the nitrogen side a little more electropositive, which I can show as a minus here and a plus here. Okay. So remember, electronegativity is this arbitrary scale. Fluorine is the high. It was set as 4. Everything else is compared to it. So as you go away from fluorine, down or left, your electronegativity goes down. Okay? And for a bond, NO versus HN, I look at my value of electronegativities, and the difference in the electronegativity determines how strongly polar the bond is. So if I look at the difference between N and O, it's 3 versus 3.5. The difference is 0.5. If I look at N and H, the difference is 0.8. 9, 3 versus 2.1. This is a more polar bond. All right, we're going to stop right there.